So now we're going to look at how that split transaction snooping bus can handle multiple transactions, and more specifically back-to-back transactions to the same cache line. First, we're going to look at a simple example. So in this example, we're going to see three transactions that happens. Transaction 1 is a load performed by CPU 1. The next transaction is a store performed by CPU 4. And the third is a load once more to the same address performed by CPU 5. So what we have here is a situation where we have a cache as well as one slice of the shared memory co-located in the same module. So it's the sum of all these memories that will constitute the total shared memory of the system. We can see that cache line A resides here to the left and cache line B resides to the right. We can also see that the cache in the middle has a shared copy of A, and the cache to the right has a shared copy of A, and the cache to the left has a modified copy of B. We're going to see what happens when you perform a load A in the system in the cache to the left. So we'll send out the read to share request, and when you send out the read to share request according to the new definition how to avoid the corner cases, that means that all the caches with a shared copy are going to raise the hand. Okay, so now we know we can't go to state E even if it is a state in Moesi kind of Snoop cache clearance protocol. We'll go to state shared, and the data will be provided from our own local memory module. But even though that happens, we still have to do the full Snoopy broadcast so everybody can see the transaction. So that one was easy. Now look at the second one. We do a store to cache line B, so B resides over here, but we also remember before that B is in state modified to the left. So what will happen here is that the left cache will need to raise its arm saying, I own it. So anybody can, with the right kind of timing, 6 cycles after the address transaction was put out on this bus. And at the same time, it's going to change its state to state invalid because this is a store operation and it's a read to write sent out on this bus. But of course, this memory module over here will also snoop this transaction and say, oh, wow, somebody wants to get my cache line because they would like to, cache line B because they would like to perform some kind of store operation. So what will happen after here is this memory request is very eager to reply to this request, so it, with the shortest possible timing, will put out the data transaction on the bus. However, after it's put out this transaction, started to arbitrate for the bus and so on, it will see that the own signal is asserted. It will notice that, and it will cancel its own transaction. So it will say it's not okay. This data transaction is not okay. I want to cancel it. I was only joking. I'm not going to provide the data to you. And instead, the cache to the left will provide the data to this request. And if right after that, the system to the right performs a load operation, that means we're going to see another read to share on this bus. The cache in the middle will raise its arm saying I own it, and change the state from modified to owned, and the cache to the right will change its state to shared. And the data will now be provided by the cache in the middle. And this situation, there was no data to cancel because this time the memory wasn't that quick to reply, so we actually managed to see that the own was asserted before it even managed to arbitrate for the data bus and so on. So it was clogged up. So this was an easy situation. So this is an example of what can happen back to back in the bus, where you have lots of different transactions and caches raising their arms and hands left and right. We're going to look at in some sense, a simpler example, but in some sense also a more complex example. First, before we do that, let's see what's happening on the bus in exactly this example here. So once more, we have CPU1 sending read to share, and the data is going to reply from by memory 1, and we're going to change the state shared. CPU4 sends a read to write request to B, and it's in memory 5, but it's actually owned by a different CPU. And the third transaction is CPU 5, sends a read to share request once more to cache line B, and it's owned by CPU 4. So what's going to happen here is that the first thing is that module number 1 is going to try to arbitrate for the bus. So that's what's happening right here. Module number 1 arbitrates for the bus for sending out the read to share request. So we're going to see the read to share request. This is the first the first transaction here, and we have the address phase starting right here. And we put, there is no collision, so we can detect that only one module tried to arbitrate for this bus at the same time. We can see that it's just one number here. So this will be what's called the fast arbitration, where the arbitration happens at the same time as you put the request on the address bus. The very next cycle, we're going to send a unique identifier of that on the same address bus. Now, since the memory module so right now the second transaction and third transaction is about to start in exactly the same cycle. So you can see module 4 and module 5, they try to start this transaction at the very same time. We will detect this because we will see both a 4 and a 5 on its arbitration signals here. That means that we cannot trust any of the data sent on the address bus because these are two transactions trying to be sent at the very same time. So this is what's called an arbitration collision. We will conclude that the second transaction will win. So there's some kind of arbitrating going on between these kind of collisions. So we know that read to write B is what's going to be sent the next time because that's what the second transaction wants to send. Meanwhile, the memory of the module 1 has detected, here's a request for a piece of data that I have in my memory module. Why don't I try to be a good boy and reply right away? So it starts to arbitrate for the data bus now. And so every other cycle you arbitrate for the data bus, every other cycle for the address bus. So this is when you're arbitrating for the data bus, you put the 1 there, and that means that after exactly 2 cycles, you will put the corresponding ID. So it puts the ID 11. So that means everybody understands that this is the transaction it wants to reply to. Meanwhile, the address transaction of the second transaction is put on the bus. So after the first collision, everybody agreed that, oh, this was a collision. Next time there is a chance to send a new transaction in 2 cycles. That's when we should put the transaction of the second transaction on the bus, the read to write transaction. So read to write B happening right here. And then the module that wanted to send the third transaction arbitrates once more in a slow mode, saying that, okay, I'm really serious. I do want to send this transaction in exactly 2 cycles. So that's what's happening here. Now we see the ID 11, so we can correlate the data that is about to be sent with the first transaction over here. And that transaction has an OK signal, so we can really trust this data. There's no canceling of data going on here. Next thing that happens is that we see the address transaction of the third transaction down here. So we're going to see the read to share request for B on the bus and the unique identifier associated with it, 51. Now, the memory module that contains the data requested by the second transaction is going to wake up and say, oh, now I realize that somebody wants to request some data that I have. So it has arbitrated for the data bus. Now it puts out the unique identifier here. So we can correlate this identifier with the request that happened over here. However, since somebody pulled the owned line, raised the owned line right here, exactly 6 cycles after that transaction started, we know that the memory should actually not reply with the data. So the memory will output a cancel signal instead of an OK signal here for the data status, which says, don't trust this piece of data happening over here. Meanwhile, board number one, which is our hero that actually owned the data requested by the second transaction, has also arbitrated for the data bus. It outputs the same identifier. It will show further out here an OK for data status, and it will provide the data and so on. So even the simple example as we showed here with 3 fairly simple transactions can, once you go down and look at what's happening in detail when you implement coherence, can create quite a lot of interesting activities. Now we're going to look at the simple example that I show you that in some sense is simple, in some sense it could be viewed as a very complicated task. We will look at a cascade of 5 stores to the same address. So we have different CPUs that all wants to store the same address. First, CPU 1 wants to store, and so it will send a read to write request on the bus with a unique identifier A. Then CPU 2 wants to store, sending out the read to write request back to back on the address bus with its unique identifier B. CPU 3 wants to store, unique identifier C, and so on, down to CPU 5 with its unique identifier F. After we've sent all these transactions on the bus, we will have a state of the system just depicting the Snoop tags as well as CPU tags that looks like this. So looking at starting at CPU 7 here, CPU 7, which was where the data originally resided, its CPU tags will be modified. It still has write access to this cache line, even though we have seen 5 read to write requests on the bus. And the reason that we still it still has the extra right to that is that the foreign read to write request from CPU 1 still sits in its input queue. It has not popped that transaction from the queue yet, so which means it has not changed its CPU tag. So it still can happily read and write the data in its cache. You can see that CPU 1 has its own my read to write request with exactly the same ID. Okay. After that, CPU 1 has a foreign read to write request with ID B. So that's a second request. So what happens here, right after it sent out its transaction on the bus, its Snoop state went from invalid to modified. The very next transaction was a read to write request to that cache line, so it changed its Snoop tag from modified back to invalid again. So now it stored a request here and it invalidated its Snoop tag. That same foreign read to write request appears as a my read to write request in CPU 2's in queue. So it has seen its own transaction on the snooping bus out here, which forced it to change state to modified. But right after that, it saw a foreign read to write request to the same cache line, so it changed it to invalid, and so on. Going all the way down to the input queue of CPU 5, which only has its own my read to write request, and it has the Snoop tag state modified because it was the last one to send a request, a read to write request for this cache line. So this is sort of the initial state, and this looks funny because we have the old system that we initially had this data in state modified still has it in state modified. It's still a writable copy. And while it's been sitting there, all these Snoop tags has changed from I to M to I, from I to M to I, and so on. And there we have yet another Snoop request that has changed its state to M. If there is a new request out on the bus for this cache line, this is the system that will raise its arm and claim that it can answer that request, even though it doesn't have the data. Actually, its CPU tag is still state invalid. So what we've done here is sort of put up a linked list of in which order we should be able to handle this request. We have a linked list with saying this foreign read-to-write request with exactly this identifier, the same as what's sitting here, is the next one to get this cache line in state modified. And the second one here that will be next in line in that queue, pointing to the input Q2, will be the next one in line, and so on. So let's see what's happening now when we try to unwind this. More specifically, we're going to see what's happening when we start to service the transaction in input Q7. So right here we have the foreign read-to-write request, the very first request on the bus. Whenever the lower Snoop protocol feels it has the time to service this request, if you look in the queue and say this is the next transaction to service, it will take it out from the queue, say, oh, it's a read-to-write request for exactly this cache line, which means it's going to change its state from modified to invalid, and also know that it will have to provide the cache line to cache number 1. So it's going to send some data with exactly the same identifier, the identifier A, to input Q1, which means that input Q1 say, gee, this is good. This is actually the first time I'm allowed to pop this transaction from the queue, because before you have the data, you can't pop it from the queue. So now it will pop it from the queue, use the data, put it in the cache, and change its state to modified. So now we actually have serviced the request in the input Q7, and by doing that, we've changed the ownership or the write permission of this cache line to CPU1. Note very well that we haven't changed any of the Snoop tags. We're still in the same situation where if there is a new request coming in, it's going to be serviced by cache number 5. Now let's service the next transaction from input Q1, because it's the only queue that can advance. All the other queues here have their own read-to-write request, my read-to-write request, but they don't have the data. Somebody has to give the data to them before they can pop those requests. So this is the only advance we can make. We do the foreign read-to-write request, we pop it, we will change the CPU tags, and also tell the CPU that it needs to send the data to the next one in line. So it's going to send it to CPU number 2, and so forth. So as you see here, we have actually first we created like a linked list in which order we would service the request, and then we unwind that list to maintain exactly the order. We will maintain the order in which the different CPUs can write. It will be the same as the order the transactions went on the bus. So in summary, we have created a split transaction bus where the transactions are serviced by each cache in exactly the order that they occurred on the bus, if at all. So each Snoop coherence protocol that snoops above, looks in the Snoop tag, is going to select only the address transaction that its cache will care about and put in the input queue. Each input queue will contain the partial bus order that it cares about, but it will be no contradictive order from the global order of all transactions on the bus. A cache will maintain its access right until it services a request from its input queue. So it should say IQ here. So it can hold on to write permission, for example, until it services a read-to-write request or these kind of funny invalidation requests from above. If you are reading a my own read-to-write request where you also pull the shared from yourself for yourself, which means it really looks like an invalidation request from input queue, you don't need to wait for the data. You can pop that transaction from your own queue and you get the write permission right away. But if you see your own my read-to-write request and your my read-to-share request where you didn't pull this magic shared, that requires you to wait for the data until you can pop that. So you will not service that request until the data has arrived. So my question here is, assuming this crazy out of order reply queue here, where we have address transaction that happens in order, but data replies that happens out of order, what kind of memory model can we really assume? Sequential consistency, total store order, or weak consistency? And it's actually sequential consistency because transactions are serviced in exactly the order they occur on the bus. Okay, so that is the defined order between these loads and stores. And the input queue will record exactly which order to service things. It's a partial order to tell the cache which order a read and write happen on the bus. So if somebody else sneaks in a read transaction before your own write transaction, that's the official order they happen on, that they happen on the bus. Okay, so if we implement a system exactly with the same coherence here, but the CPU has a store buffer, which memory model is the strongest model we would implement in that situation? And that is the total store order, because total store order, we allow loads to bypass stores, but and if we have a sequentially consistent coherence on top of that, that means that we're still going to lose the strongness of the sequential consistency because the